Okay, so what we're going to be looking at is we're going to be looking at piecewise functions, and we've already sort of started this at the start of this lesson, but we're going to be looking at piecewise functions, and we're going to be figuring out if f of x is continuous at x is equal to a. So what's going to happen is three things must occur for our function to be continuous. So the first thing it says is f of a must exist. So what that means, this first bullet, is the point must exist. There can't be a hole. So for example, if I gave you a graph, and let's say this was my graph right here, and I say this is a, and that's 4. And I say, what is f of a? So f of a, the y value, when x is a, the y value is 4. The point exists on this graph, right? The point exists. So f of a is equal to 4, we'd say the point exists. Versus, here's an example where the point wouldn't exist. If I put a hole here, f of a does not exist, okay? So the point has to exist. The second thing is the limit must exist. So the left-hand limit must equal the right-hand limit. So in this case, the limit exists, right? The left-hand limit is equal to the right-hand limit. So I'd say the limit as x approaches a from the left of f of x is equal to 4. The limit as x approaches a from the right of f of x is equal to 4. Because the left-hand limit equals the right-hand limit, the limit exists. And the limit as x approaches a is equal to 4. And then the third thing for a function to be continuous is the limit must equal the point. So what that means is my point was 4, my limit was 4. If those two answers are the same, then the limit equals the point. And we have all three of these things occur, we're going to say our function is continuous. Okay, so all three of these must occur for our function to be continuous. So what I want to show you is we're going to do the algebra, and then I'll prove it to you by graphing. You do not have to graph on your test, though. Okay, so for this one here, we want to know if our function is continuous at x is equal to 0. So this is always our potential breakpoint of the graph. And we want to know, is our function continuous at x is equal to 0? So the first thing we always have to test is, does the point exist? What I would be checking is I would be checking what is f of 0. Is there a, can I plug 0 into one of these two functions? Now, we have to decide which function we'd be plugging 0 into. Do you know what function we'd be plugging 0 into? The first one is less than or equal to 0. This guy is greater than 0. So which is the only function I could plug 0 into? The top function, because of this greater, less than, or equal to 0. So I'm going to plug my point into this first function. So f of 0 is going to be 0 squared, and that is equal to 0. So f of 0 equals 0. That's a point on the graph, 0, 0. The point exists. Okay. Second thing we need to check is, does the limit exist? So does limit exist? We did this yesterday. So in order for the limit to exist, we are checking the limit as x approaches 0 from the left, and we have to decide which function do we plug that into. So Kayla, what function would I plug, like which would be my left-hand limit, the top one or the bottom if I'm approaching 0 from the left? It'd be the top one. This would be my left-hand limit, and this would be my right-hand limit. So limit as x approaches 0 from the left of x squared, which is equal to 0 squared, which is equal to 0. Okay, now I need to approach my limit as x approaches 0 from the right-hand side. So right of 0 would be the right-hand limit. So I'm going to plug it into x is my function. Plug 0 in, and we're going to get 0. Does the limit exist? The limit exists if left-hand limit equals right-hand limit. So what do you guys think? Does the limit exist? Yes. If you get the same number, then we have left-hand limit equals right-hand limit. Therefore, the limit as x approaches 0 of f of x, it is equal to 0. Okay, so the point exists, the limit exists. For it to be continuous, the third thing is the limit has to equal the point. So the point that we had was 0, and the limit that we had was 0. If they're the same number, then what we could say is we could say the limit as x approaches 0 of f of x, it is equal to the point, and it was equal to f of 0. These two gave us the same answer. So the limit equaled the point. Therefore, our concluding statement is all three of these are true. Then what that means is the function is continuous at x is equal to 0. Let's prove this by graphing it, right? So if you're good at graphing, we're going to see this by graphing it. So if I was to graph this, I just want you to do a little tiny sketch for your graph. This is a parabola, and you know that a parabola would look like this, but it wants me to only graph the piece of my parabola less than or equal to 0. So that would be this piece of my graph. Right, my parabola would start there. We know that this is a linear function, which looks like this, but they want me to draw the piece of the graph that's greater than 0, so this piece of the graph here. Now, it looks like it'd be an open circle, right? Like normally we'd have an open circle, and then we'd have my linear graph, but the circle's actually going to be closed in. Because of this parabola, it was touching 0. So this is my graph here. Continuous means, can I draw that graph continuously without lifting my pencil? And I could, right? There's no holes or breaks in this graph. What it's asking is as x approaches, so does the point exist? Yes, the point at 0 exists, it's right there. Does the limit exist? Yes. Left-hand limit equals right-hand limit. The limit is 0, and then the limit equals the point. Okay? Let's do class example 2. And again, you might not have enough room, so if you're tight for room, you could do this one on a separate sheet of paper. Okay, so first thing you got to always check is, does the point exist? So f of 1. So how I know I'm testing 1 is because at 1, there's potential breakpoints in my graph. There could be jump discontinuities or holes or something. So f of 1, we need to decide where we're going to put f of 1. Oh, and which function, the top function or the bottom function, are you going to stick 1 into? The bottom, because it's the one with equal to 1. So this function here, x minus 1, which will be 1 minus 1, which is 0. So f of 1 is equal to 0. The point on my graph when x is 1, y is 0. The point exists. There's going to be a point at my graph at 1, 0. Second thing we're going to check, does the limit exist? Okay, so in order for our limit to exist, we need to check the limit as x approaches 1 from the left. And Nick, which function would I punch in my left, which is my left-hand limit, the top or the bottom one? So approaching it from the left, which is a number less than 1. Top limit. This would be my left-hand limit, and this would be my right-hand limit. So less than 1 would be this guy, x squared plus 1. So we'll plug in our 1. And we're going to get 2. Now I need to find the limit as x approaches 1 from the right-hand side. The right-hand limit would be x minus 1, which would be 1 minus 1, which is 0. Does the limit exist? No. I don't even need to go to number 3, right? Because number 3 is the limit equals the point. The limit doesn't exist. This function is not going to be continuous. So we'll write down the limit as x approaches 1 of f of x does not exist. Okay? So that means like I said, I don't even have to check step 3, the limit equals the point, because the limit doesn't exist. So, and then we'll draw this to see. I know that f of x is going to be discontinuous at x is equal to 1. Something's going to be happening at x is equal to 1. So let's do a quick sketch of this graph and see why that is. And again, you do not have to sketch this on a test, right? I just want to sort of show you visually the reason behind this. So if I was to sketch this one, okay, x squared plus 1 is a parabola going through 1. Now, I want a graph where x is less than 1. So I need to find what's my point when x is less than 1. If I put 1 in here, do you know what my y value would be? So like if this guy is 1, what's this value? It'd be 2. Yeah, because if you put 1 in here, 1 squared is 1 plus 1 is 2. So this guy would be 2. And I only want the left of 1. So basically what I want is an open circle here. Okay, and that would be my parabola. Now, this graph is a linear graph that goes through -1. So y-intercept of -1, which would be right here. And then it's got a slope rise of 1, run of 1, right? The slope is 1 over 1. So the linear graph would go here and then here. This would be my linear graph. And they want me to graph when x is greater than or equal to 1. So again, if I put 1 in here, 1 minus 1 is 0. So it would just be this piece of my graph right here. Okay, the point exists at 1. This is my point right there. The point exists. There is a left-hand limit. It's 2. There is a right-hand limit. It's 0. But the limit doesn't exist because left-hand limit doesn't equal right-hand limit. The function is discontinuous at 1. This is jump discontinuity. Okay, let's go even more complex, and then this is as complex as we would get. Okay, so we've got 2 potential breakpoints based on my piecewise notation. Do you know what the 2 potential breakpoints that we'd have to check are? 0 and 3. So just on my number line, 0 and 3 is what we're checking. And I get them from the inequalities over here. Okay, so first let's check x is equal to 0. We're going to check, is our function, sorry, not 3, we'll do 0 first. Is our function continuous or discontinuous at x is equal to 0? we've got to do all the work. We have to first find if the point exists. So I need to plug in f of 0. Now, I have three functions, 1, 2, and 3. Do you know which function f of 0 is going to go into? It's going to go in function 2 because of this greater than or equal to 0. So f of 0 is equal to 1. That's what it's equal to. Okay, so what that means is that's a point, 0, 1. Point exists. Step 2, does the limit exist? So we need to do the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. Limit as x approaches 0 from the left. Alex, which function would I plug it into? Function 1, 2, or 3 would be left of 0. The first one. Yep. Left of 0 is a number less than 0. So it would be this function here, x squared minus 2. We're going to plug in 0. And we're going to get negative 2. Okay. Let's do the limit as x approaches 0 from the right. Shaywa, what function would I choose for 0 from the right? Number 2, yeah, which would be this function here, which is 1. What's the limit of a constant? The constant. Does this limit exist? No. So I just got to say left-hand limit does not equal right-hand limit. Therefore, the limit as x approaches 0 of my function does not exist. I don't need to go on to step 3. And I get to say my function, this graph is discontinuous at x is equal to 0. Okay. So there's probably, if we graphed it, we won't graph it, but there's probably like a jump discontinuity or something's happening. Okay, now we have to check 3. That's another potential breakpoint. First, does the point exist at f of 3? Akil, which function would I be plugging f of 3 into? The third one, this guy right here. 4 minus x, so 4 minus 3 is equal to 1. Point exists. On this graph, there's a point at 3, 1. Does the limit exist? Limit as x approaches 3 from the left. Sean, function 1, 2, or 3, which one would be approaching 3 from the left? Which one? Yeah, the middle guy there, so 1. Limit as x approaches 3 from the left of 1. The limit of a constant is the constant. Okay. Limit as x approaches 3 from the right would be this guy here, greater than or equal to 3. So it'd be 4 minus 3. I should actually write what function that is. 4 minus x. Left-hand limit equals right-hand limit. The limit exists. And I could say that the limit as x approaches 3 of my function, if I was to graph all 3 pieces, it's going to approach the y value of 1. Does the limit equal the point, Alex? So step 3, is like, so the limit we got was 1. What was the point we got, the y value on the point? 1. Does the limit equal the point? Yes. So what you could say for this one is the limit as x approaches 3 of f of x is equal to f of 3. And actually, I could even say that was equal to 1. The limit equaled the point. The limit was 1, the point was 1, they're equal. Therefore, f of x is continuous at x is equal to, what were we checking? 3. So it was discontinuous at one point on the graph, continuous at the other point on the graph, but overall, discontinuous here, continuous here. Okay? Your homework, and actually the homework that I want you to, I think, start with is these questions. And I believe they were 8, 9, and 10. So, and again, I drew the graph. Maybe it actually says for B, it says you have to. On your test, you wouldn't have to, right? You just have to do does the point exist? Does the limit equal the point? So 8, 9, and 10. Let me just see what the other questions were. Oh yeah, you'll still want to do so do all of the homework. Question 1, you're going to have a graph on your test like this. It's going to be worth 6 marks. Do question 3. And yes, so that's your homework. And then we'll talk about